In Chapter 5, we used a phrasing called real numbers, and I described real numbers as the numbers that you can count on a number line, and I compared them to the imaginary numbers, which you will experience when you get to Algebra 2 and beyond. Since both integers and radicals make up the set of real numbers, or they're parts of the set of real numbers, there are other things as well. We're talking about the operations within the real number set in this lesson. You won't really concentrate on what we're going to be talking about very much in Algebra 1. You're mostly going to be using it in Algebra 2, but since it deals with radicals, it makes sense to introduce it to you now. There's a property within any set of numbers, and it's called being closed. And a set of numbers is closed under any particular operation, add, subtract, multiply, divide, or whatever your operation is, when the operation performed on any two numbers in the set results in a number that is also in the set. So here's a for example. The set of integers is closed under addition, subtraction, and multiplication. What that means is that if a and b are two integers, so just two general integers, positive, negative, whole numbers including 0, then a plus b, a minus b, and a times b are all integers. So no matter what two integers you pick, the sum will always be another integer. No matter what two integers you pick, the difference will always be another integer. Whatever two integers you pick, the product will always be an integer. There are no two integers that you can pick that when you add them, you won't get an integer. Now, you could divide and you would not get an integer, or not always get an integer. So, for example, 10 divided by 5 is 2, and 10 is an integer, 5 is an integer, and 2 is an integer. But 10 divided by 3 is 3 1/3, and that is not an integer. So because you don't always get an integer, division is not one of our closed operations. Last year, you performed operations on rational numbers, and a rational number is a number that can be written as a fraction or as a ratio, where the numerator and the denominator are both integers, and obviously the denominator can't be 0 because then it's undefined. An irrational number cannot be written as a ratio of two integers. So you'll see examples when we get down to example 2, which will start throwing in some irrational numbers, and radicals, most radicals, are irrational. In decimal form, which I don't encourage you to use decimal form, but if you're looking at decimals, a decimal rational number is going to either terminate or repeat. So if you have a decimal value and it terminates, like 2.6, then it's rational. If you have 2.3 repeating, then that's also rational. If you have a decimal, like, for example, pi, that's one of our famous irrational numbers, that has no pattern and it doesn't terminate, so therefore that's an example of what it would be like to be irrational. So example 1 has all rational numbers, and we're adding them, and we have to figure out whether the answer is rational or irrational. So I'll start you off, and then you pause the video and finish the table. 12 plus 5 is 17. And could 17 be written as a fraction? Not what is it, could it? And the answer is yes, it's rational. Because if you wanted to, you could write it as 17 over 1. Now, do I really care what it is as a fraction? No. Do I care that I could write it as a fraction? Yes. I'll do one more with you. -4 plus 9 is 5. Could you write 5 as a fraction? Yes, you could. 5 over 1. But do I really care what it is? No. Just that you could do it if you wanted to. So pause the video and finish the chart. Check your chart with mine and answer the critical thinking question on your own. When you're ready, let's check out example 2. Now, this example isn't about closed or open because you can't check closed or open when you're talking about two different sets. And if you looked at the title of this example, it's rational and irrational. So we're not really going to talk about closed because you can't be closed when you're two different sets of numbers. But let's look at some patterns that will start forming as we go through the next three examples. So let's add up some rationals and irrationals. And then you should be stumped because you can't combine a radical and an integer. I hopefully taught you that, and hopefully you are realizing that. So you just write 1 plus the square root of 5, and that's the answer. And if you were to type that in your calculator, square root of 5 plus 1, you would get an irrational number because you'd get a decimal that does not terminate or repeat. Now, what's interesting about the square root of 2 plus 5, 6 is you can actually kind of combine them a little. If you put the square root of 2 over 1, and then you get a common denominator, you'll get 6 radical 2 plus 5 all over 6. Now, that's not really super friendly, but remember, if you can combine things, you should. So I'll write that as my official answer. Oh, whoops, I wrote it wrong. Either way, if you were to type this in your calculator, you'd get an irrational number, you'd get a decimal that does not terminate or repeat. 4 plus pi does not combine, so that's also irrational. And if you want, feel free to check these in your calculator. And same thing for negative 8 plus the square root of 10. They don't combine, and so they end up being irrational as a sum. Try the critical thinking question on your own. When you're ready, let's move on to example 3. So again, you can have your calculator handy and type these in, but I'm going to write them as radical versions. So 6 radical 12 can actually reduce. So I want you to practice reducing radical 12. Your final answer should be 12 radical 3. I'd like you to pause the video and prove that you can get 12 radical 3. That's a skill from the pre-6 and also the 6.1 lesson. If you can get that, then I feel confident in you, and you can write that the answer is irrational, because if you type in 12 times the square root of 3, you'll get a non-terminating, non-repeating decimal. Negative 2 times pi just gives you negative 2 pi, and that is irrational. 2/5 times radical 3, well, if you put the radical 3 over 1, you'll get 2 radical 3 over 5, and if you type that in your calculator, if you're not sure, that is irrational. But don't get ahead of yourself, because 0 times the square root of 6 is 0. Anything times 0 is 0, and that is rational. So maybe that just blew your mind, but what do you think about the critical thinking question? When you're ready, let's check out example 4, which might blow your mind a little more. Here we've got some irrational numbers. They're all irrational if you look at the chart, and we're going to add and multiply them. 3 radical 2 plus 5 radical 2 is 8 radical 2. Remember, treat it like 3x plus 5x, and that is irrational. Radical 12 plus radical 27, both of them can be reduced. I want you to pause the video and reduce it. Prove to me that you can do it, or prove to yourself. You should end up with 5 radical 3. If you got 5 radical 3, great job. and that is irrational. Square root of 7 plus pi, well, that's like adding an x and a y. You just can't do it. So you just get square root of 7 plus pi as your answer. And that is irrational. And remember, you could also check these in your calculator, checking for the decimal version, but I would love for you to know that without checking the decimal versions. And check out this. Negative pi plus pi is 0. Anything plus its opposite is 0, and 0 is a rational number. Whoa, our first rational. Pi times radical 7 is pi radical 7. It doesn't combine, and that is irrational. Square root of 5 times the square root of 2 is the square root of 10, and that is irrational. 4 pi times radical 3 is just 4 pi radical 3. You can't combine them, and so that is irrational. And our last one, radical 3 times radical 3, is radical 9, which is the number 3. Whoa! That's our second rational answer. So try critical thinking on your own. Numbers 1 and 2. If you have any questions, write them down and ask me when you come to class.